Hello, good afternoon. How's everybody? My name is Tamika Jacques. I'm working for Avangrid. I'm going to be the moderator of the panel. No, not seriously. But I am pinch hitting for my colleague and friend Tamika, who unfortunately I think today is under whatever, some type of medical situation, and probably that's too much for me to say anyway. And Tamika, sorry about that. But that's just the penalty for picking me, Bruce Carlisle, with the Massachusetts Clean Energy Center to pitch hit late last week. So we're not here to talk about Tamika or myself. We're here to listen to a panel of experts talk about their work and their projects sponsored by Now RDC, and to have a little bit of a conversation around localizing this massive supply chain that we're going to need to be able to pull off this industry here in the U.S. So a few points to note, just to sort of tee this up. We've been at this for more than a decade. Lease sales, all the work that went into prior to lease sales in terms of site identification. All the work that developers with site control have done on their permitting and consenting and their, all of their surveys and all of their, engineering. And we are now building Vineyard Wind 1 and South Fork out of New Bedford and New London, respectively. This is a great, great moment. Yet there's a little bit of sort of color around this moment. You've sort of heard this. And that's, a little bit of the sort of uncertainty that, some of the global macroeconomics and sort of offshore wind specific supply chain issues have presented to developers. Notwithstanding that, I think many of you are here because you share the long view, as I do, that in order for many states and many regions of the U.S. To meet our clean energy and climate goals, offshore wind is going to be critical to our energy future. So it's really not an if, it's sort of a when. And yeah, there's some bumps in the road, but I think we'll come out the other side. Just to sort of set the stage, and Biden national goal, 30 gigawatts by 2030. State procurement mandates 43 gigawatts by 2040, and state planning targets of 112 gigawatts by 2050. So that's pretty robust pipeline. But is it sufficient for manufacturers and fabricators and new market entrants to be able to make the investments and get the uptake they need? So I'm here with excuse me, Walt Musial, Eric Sells, and Srikar Karnati. They're each going to do a presentation, and then we are going to gather, and I'm going to ask them a few questions to get the discussion started, and then we're going to open it up to you guys through the Slido app and see what questions you might have. So I'll have each of the speakers briefly introduce themselves, and we'll start with Walt, who's pitch hitting for Matt Shields from NREL. Walt, you want to take it away? Yeah. I mean, you can do it from over there, but...
I'll just stand up. I'm Walt Musial. I'm Chief Engineer at the National Renewable Energy Lab. So I get involved in a wide...
Sorry, 1 second. They can't hear you on screen.
Yeah. Come on over and just, you can go right into your slides or whatever and
Okay, so
just do
you
your
wanna
presentation.
Do the introductions as we do
Yes.
our presentations? Okay.
Yeah.
Sounds good.
Yeah, you can tell we rehearsed this really well.
Yeah, this is how we should do it. All right, now everyone can hear me. I'm Walt Musial. I'm the Chief Engineer at the National Renewable Energy Lab for Offshore Wind. And I am pinch hitting for Matt Shields, who is our lab expert on supply chain and supply chain issues. Matt came down ill yesterday and regrets that he can't be here today. So I'm going to do my best to give his presentation and fill in the ideas that he wanted to convey today. And I guess I'll just dive right into it, Bruce, right? I'm happy to be talking about the supply chain, and I think it's one of the most important aspects of offshore wind development that kind of gets ignored, although when we survey the constituents of the National Offshore Wind R&D Consortium, almost everybody says supply chain is like their number one, and for good reason, because these projects are that we've committed to, 30 gigawatts by 2030, all the state commitments, they all depend on the industry building this pretty huge supply chain that is not part of the cost of energy of the projects themselves, and the cost allocation of who's responsible for building that supply chain is not set in stone. It's not a guarantee either. So, but nothing's going to get built if we don't build the supply chain. We have to have a supply chain, at least leveraging the European supply chains, which are in high demand. So this is a critical issue for the industry, and I feel like, you know, this panel, hopefully we can shed some light on some of the stuff that's going on with this. If I click this, are my slides in line? I'll find out, I guess. Here it is. So today I'm going to talk about this project that Matt's been working on, and it's a collaboration called Smart Power Workforce and Supply Chain Analysis that really builds off of a previous project that they finished in, I think, January this year, called the Supply Chain Roadmap, that was published, and it's on the DOE website. And so this is an extension of that, but it's really focused on the four or five mid-Atlantic states, Delaware, Maryland, Virginia, North Carolina. Hopefully I got them all. And those are the name that they gave to themselves, the Smart Power States, and it's looking at the regionality of this building this supply chain. And this slide just shows the 7 areas where the original supply chain roadmap identified as being challenges for building the supply chain, the investment risk, how can we address that, the siting and technology challenges of locating all the different types of facilities and the supplier networks that are required to build that, ports and vessels that everybody knows about, limited workforce that in those areas, and we're not trained to do this stuff yet. We're just learning ourselves. The cost competitiveness of the industry and ensuring that the communities that are affected by this receive equitable and sustainable treatment, and that we don't repeat some of the mistakes of the past in how the energy industries have evolved in those regions. So that's the kind of thing that we're looking at. But now, as we just continue to go back and look at that supply chain report, there's the estimate was about that there would be a requirement for about $22.4 billion of investment in that supply chain. I actually think that's a low number. I think we're going to need a lot more than that, especially if you start counting all the grid upgrades that we're going to need to build. It's probably going to be something like double that. But we need to track these investments and the requirements that are necessary to get us to both to the numbers of the investments that have to be made and the jobs that will follow that, both in the tier 1 suppliers, but also down the chain into the tier 3 and 4 suppliers that are there in some form. And we looked at the existing manufacturers in the United States across multiple states and found that there was extensive opportunities already in place in a lot of these states, especially in some of the coastal states, where we could leverage the existing manufacturing, especially for the lower tier suppliers. It's the tier 1 suppliers, the big ports, blade manufacturers, turbine suppliers that we don't have right now. But a lot of these other industries are more adaptable because they don't require as much infrastructure investment. So this project builds off that framework that was provided by the supply chain roadmap, published, I think that was maybe in January this year, and I encourage you to retrieve that report and look at it. Of course, the world has changed since January, and it continues to change, and this report, this study, is going to do its best to try to keep up with those changes. So it's going to build on the existing capabilities that exist within the region that we know about, and it's going to complement the other activities that are going on in the East Coast. And it will position the smart power states, which are the Central Atlantic region, to support the near and long-term offshore wind developments in a regional way, which is not typical. A lot of competition right now, still state by state, rather than developing that regionality. And it develops an equitable way to provide those benefits and jobs to the local communities that might be affected by the development of that infrastructure. So that's where we're focused at. The project really breaks down into two complementary reports. One looking at the workforce skills and assessment of those skills based on the types of infrastructure and labor that will be necessary to build out the supply chain and to build out the projects, and also just a supply chain assessment of what facilities need to be built. And so those will be published in separate reports, anticipated late in 2024 coming up. More detail on that is in the detailed workforce assessment. First, we break down the types of labor that will be needed in the different categories. And here we show some examples of the production engineer, the welder, and the crane operator, and how those play out into numbers of workers and the types of qualifications that will be necessary, so that we can build programs to train those workers in the necessary way in the local regions where they will be living. And then we'll be looking at the supply chain. And then this is just showing that, we're projecting out into the future. This shows out to 2033, but there's different demands that might occur, and it's affected by different factors in the supply chain and in the demand and the way that policy is structured around them. So we'll be looking at different scenarios that are occurring, and also the impacts of the current situation that we see before us today in the industry, with a lot of off-take renegotiation going on, and how those projects, when they're renegotiated and rebid, will affect the timelines and the costs of those projects, and the macroeconomic conditions that associate with them are really important, because we're watching inflation possibly coming down, with the expectation that maybe interest rates will also come down, but we'll still have these supply chain issues to manage as we go forward, and we'll be looking at those scenarios in terms of different ways that these might affect each other, including the technology evolution, which is vital to this consortium, which is focused on technology innovation, which we will always need as we go forward, and that's a big layer that kind of gets put on top of that. But the key is to understand how all these factors kind of put together will combine to attract or dissuade investors from coming in and building that supply chain, which is not part of the project LCOE. But it certainly will affect the LCOE if they don't build it, or if they do build it, and they have to build it in sufficient quantity so that it works. So I think this is my last slide, but this chart on the right shows the increase in cost, and I really think this is understating some of the problem, because it really doesn't consider the possibility or the fact that the supply chain is still immature and needs to be built. But you can see that interest rates do have the biggest impact on raising the assumptions or the cost of the projects. But really, what we found is that, if we're looking at this, the regionality and building a regional supply chain is going to have some advantages in getting cost of energy down and in making those supply chains more efficient. We'll look at how the advancement of the supporting supply chain in the U.S. and the regional coordination and communication can address that. Of course, we're still going on, but there's boom and bust cycles that will be created by delays in production and development processes. If a project gets canceled, it affects not just that project, but it affects the other projects that are depending on the same supply chains. So we have to look at those in terms of the big picture, and some of that will be part of the study that we're looking at. So I'm going to, before I get into areas where I haven't been involved, I'm going to stop there and let the other speakers go, and we'll pick it up again when we do the Q&A. Is that how you want to do it, Bruce? That's perfect. Okay, good. Yep. All right.
Good afternoon, everyone. My name is Srikar Karnati. I'm a senior research engineer at the GE Research Center up in Niskayuna, New York, Albany, New York. Today I'm going to talk about the program we have at now at DC on weld assembly of large castings. So before I get into that, GE is one of the leading offshore wind business out there with an offering of offshore wind turbines starting from 6 megawatt to 14 megawatt. So our largest is the Halyard X with a 63% capacity factor. So it's got a rotor diameter of 220 meters and a blade length of 107 meters. So it's an enormous structure. We also have the Halyard 150-6 megawatt wind turbine. So that's been running in Europe and in North America. So the topic specifically I want to touch upon is the size of these wind turbines, how big these are, how massive these structures are, and kind of focus on the challenges pertaining to building such large components. So this is a slide that I like to use, which paints a very nice picture of the scale and how enormous these structures are. And we have some interesting scale bars here that you could compare against the wind turbine. So in the middle of the chart here, you have the Halyard X, the 13 megawatt version, and there's a good comparison of how it ranks against Empire State Building and Eiffel Tower, London Eye. So these are really massive structures that we need to build and move to the locations, and most of them happen to be across the shoreline, so offshore. So transportation is a big challenge. Logistics, material handling is a big challenge. Now, the topic that I want to concentrate the discussion on is around castings and large structures. So we'll stick to the nacelle and what's up tower. Here are a few images of from the manufacturing facility of GE, where these are made in Saint-Nazaire. So you can see the scale and of how big these structures are, assembling them, getting them prepped for shipping, and then getting them to the assembly plant and eventually offshore to the install site. So here is another picture of how they're handled, how they're loaded and kind of transported, right? So what I want to really focus on, again, I keep coming back to this, is the size and scale of these castings. So the castings could be, you're talking about hundreds of tons of steel and ductile iron in per casting. You're talking about dimensions that span anywhere from 3 to 9 meters, so very enormous structures. Now, making them itself is a huge challenge. So there's a lot of engineering problems that need to be solved, and there's a lot of expertise and tribal knowledge that goes into making these castings. Additionally, how do you transport them, right? So 4.5 meters is kind of the thumb rule when it comes to transporting them on road. So how do you make these gigantic structures? How do you get them across? Do you fabricate them onshore. So you're talking about an onshore foundry. So a lot of these questions need to be thought about, how you fabricate them and ship them, right? And now the discussion becomes even more complicated when you're talking about localizing this manufacturing to the United States, right? So most of the castings that are made today are overseas in Europe and in Asia. And if you were to bring them back to the United States and start localizing this manufacturing, what are the challenges over there, right? So the vision, right, and this project that I have with Now ADC right now on weld assembly of large castings looks at a very important but a small portion in the larger strategy of this. But for us to localize these wind castings, I think there are very few foundries in the United States right now, that maybe a handful, that could actually cast these components domestically. So with those handful foundries, it's almost impossible for us to kind of scale up to the range we want, especially speaking completely, with the domestic supply chain, right? On top of that, if we wanted to cultivate a larger supply chain, factoring the infrastructure we have today, what could be done, right? So this welding of large castings was an approach that we were exploring to cultivate a supply chain that can survive off smaller infrastructure. So there are a lot of smaller scale foundries domestically. So the thought was, if we were to segment these large castings into smaller castings, could we fabricate them, weld them, and join together to build the final structures where the assembly plant is. So on this program, we're exploring the techno-economics around what does it cost to make these castings, what is the cost involved in transportation and logistics. So given the massive scale of these offshore components, so the transcontinental shipping and the logistics cost associated with that can be significant, and particularly if you factor the tariff and other policy-wise upcharges we have, that creates further opportunity for us to localize casting to the United States. So in this program, we are looking at that techno-economical analysis. Parallel to that, you're also exploring the technical feasibility of doing something like this. So this gets a little bit technical, but the ductile iron, the casting, most castings are made out of, is not particularly a weld-friendly material. So you often have to follow through what's called a post-weld heat treatment, where you put the entire part inside a furnace to temper and recover some of the toughness that is lost during the welding process. Now, imagine a component that is as huge as an offshore casting, putting that inside a furnace, and then following a heat treatment, right? So it becomes almost impossible. So the qualification of this kind of a process is also a huge challenge. Now, we are starting with a pretty ambitious vision of using welding as an assembly for these large castings. This is a kind of a high-risk, high-reward effort to kind of simplify the logistics, but looking at the more immediate cross-cutting advantages of qualifying welding of castings for offshore purposes enables repair of castings. This can help us improve the yield of the castings itself. So as I was saying previously, there's a lot of engineering complexity involved in fabricating these large castings, and that can, of course, affect the yield of the casting process itself. So what we are trying to solve in near term with this program is that, address qualification of this process. So we've partnered with DNV to come up with the qualification and certification methodologies. Right now, the methodologies also don't exist for certifying the welding process. So we're doing that on this program as well. So that's kind of the gist of what I want to talk about. So happy to answer any questions during the discussion shortly. Thank you.
Hello. My name is Eric Sells. I'm a senior engineer with Keystone Tower Systems. Little history, actually it's in my slide pack here. So Keystone Tower Systems, if you're not familiar with what we do, we manufacture towers that support the turbines. We have an innovative approach to this. A typical tower is made out of cans that are basically egg-shelled together in the offshore space because everything's so large. They basically have, like I said, eggshell. You stack these cans and then weld them together. Ours is a continuous manufacturing process where we perform a cross weld. So this would be the cross weld, also shown here. It travels with this long ribbon of steel that feeds into a simultaneous bend and helical weld system. And so you feed in this ribbon of steel, and out the other side comes a completed tower. It's worth noting that spiral welding technology is not new. It's been in the industry, like gas lines and water lines fabrication for many years. The innovation is being able to actually taper a section, so a non-cylindrical section. Most of this slide pack is going to be kind of in the technical weeds, so and that's kind of where I like to reside. But I'll try to pull out and talk more to the supply chain issues, and this is kind of an ode to that. So in the near term, we would essentially deploy our existing technology with a little bit of upscaling of the welding technology. So our current supply chain, just to be clear, we're on the onshore space. There are not offshore domestic tower suppliers in the U.S. So our near-term play is to essentially be manufacturing tower tops. And so we've actually had active discussions with OEMs, developers, and foundation suppliers to move that scope split away from the transition piece and further up the tower. So Keystone could supply tower tops, and monopile suppliers could supply tower bottoms. So that's kind of a segue into this. So this NowRDC project was funded primarily to look at the difference between conventional single wrap tower and a way to more efficiently scale up the technology to a multi-wrap tower. So the single wrap version would be a very heavy wall thickness monolithic piece with much larger bending forces and kind of an absurd amount of weld passes to actually weld these things together. Or the multi-wrap process would be multiple handling and putting that through our helical weld system more than once. But the bending forces go down, you're actually producing much less weld volume, and so the whole process moves much faster. That also unlocks our supply chain. Currently there's, as far as I know, one supplier that's going to be supplying like these very heavy plate thicknesses. We could use this with coil supply chain, which is abundantly available and much cheaper. So I'm going to go into some of the details on this. It's maybe worth seeing where the NowRDC money is going, seeing what the benefits are here from the research. And so, yeah, here's some analytical discussion points. So some discussion about the finite element models for buckling analysis. And so what we've modeled is and I should give credit to Johns Hopkins University, Ben Schaefer, for PIing this part of the research. So this is a two-layer tower, sort of unwrapped into a two-dimensional plane, and the blue layer is offset from the cyan layer by 180 degrees, or half of a sheet width. So going back up to this, the second layer would basically be offset by half of this sheet width. And that detail shows you'd have sort of staggering of helical welds. And so what you'll get is two different layers with two different weld flaw geometries and conflicting buckling patterns, which would be a good thing. so they don't buckle simultaneously together. And so the output of this research is that just through helical welding of the plates like this, when benchmarked against a monolithic tower, you could expect about 75% of the buckling capacity. Adding in some structural adhesives, you can get up to 100%. And what the models are showing is that structural adhesive does not actually have to be all that strong, just some very moderate off-the-shelf type adhesives could achieve that. And then Andy Myers over at Northeastern University has been doing some scaled down buckling testing for us. We have not seen the expectations, but I would say mostly this is all attributable to small scale fabrication issues. So you can see these relatively large weld beads, and you can even kind of see some of the flaws that exist just from the cold shrinkage of that weld. And so they did buckle prematurely. We've subsequently sort of redesigned these samples and used adhesives only, so to avoid the small scale fabrication issues. And we are seeing this 100% buckling capacity as we would have expected. And here I sort of talk more about the small scale effects of fabrication. So this top image is from our weld development of fatigue testing, which I'll talk about next. And so these are 1/2-inch thick plates. You can see a gap exists between them. There's two-pass weld, and you can see the heat affected zones, all that good stuff. But you can see the relatively high thickness to gap ratio, and you can see very little distortion between the layers. Whereas what we've seen on these small lab scale multi-rep samples is this very large weld bead relative to the wall thickness, and we're getting all these crazy shrinkage distortions. And so, and then this bottom image is the unwelded and adhesive only sample, which is obviously not distorted at all. So what we're going to do is perform more of these adhesive-only tests, and then try to engineer spacing between the adhesive layers so that we can replicate an adhesive unbonded region and see if we can induce buckling within the unbonded regions and vary that gap spacing. So I'll talk some more about fatigue. So again, this NowRDC funding has enabled us to develop a multi-layer weld procedure, which I show here. You can see I put in some dashed lines to show the layers, which are not very easily discerned otherwise. So this actually is not a monolithic piece, it's 2 layers. This is it was a V joint butt weld that was welded into a continuous bottom layer as backer. So after we developed that weld, we did some destructive testing. We saw ductile behavior at the notches of the weld, and then produced panels from which we would cut dog bone samples. And here are the details of the dog bone sample. So the middle weld is actually a double-sided weld, just like our conventional tower would be. And so that's weld number 1 and 2. We offset from that a weld just like this. So it's welding into the bottom layer as backer, and offset the other direction and welded a 4th time by welding that 3rd layer into the backer. So each one of these samples actually has 3 welds that are being tested, one of which is a double-sided weld. So here is a test that was conducted on one of these dog bone samples to failure. There are a couple of key points in the test. So we stopped it at crack initiation, this particular sample went to about 400,000 cycles until this crack initiated. We stopped the test at rupture of the first layer, and then stopped it again at rupture of the second layer. And then by the time we got there, the third layer just plastically yields. So there are no cycles to perform for fatigue testing. One of the interesting things, we were theorizing that this would happen, but our test results actually do confirm it. It is basically we're seeing a natural crack arrestor in the multi-layer system. So what you would expect from a monolithic test is if 1/3 of the cross-section was already consumed with a fatigue crack, that you would actually see a very short number of cycles to full rupture. But what we saw is from crack initiation to rupture of the first layer to subsequent initiation and rupture of the second layer was actually twice as many cycles. And from all the tests that we performed, the average was actually about 6 times as many cycles for that second layer than the first. So we've got a natural crack arrestor and a little, I think the important part of this is once the structure is actually deployed, you'd be able to observe through accelerometers and instrumentation of the turbine degradation in the stiffness of the tower. You then be able to stop, halt the turbine, put it in park, and deploy some O&M, maintenance to go look for cracks and find them, repair them, and not have catastrophic failure of your tower. You'd have a basically resilient system that's robust against catastrophic failures of this sort. Some other test samples, this was one that was kind of an anomaly. It actually ruptured in the middle layer first. We had some porosity, as you can see, but it's actually kind of worth noting this was strangely an outlier on the high side. So it was actually this data point, which was found to be an outlier. So even though we had this kind of gross amount of porosity in this middle layer, it actually was an outlier on the high side of cycle count. And so, yeah, after I did some analysis on our test results here and found that this actually failed as a design category, 80, and which was our target of this. There's a design detail of a weld into a backer, and that would predict a design category 71. And so this is higher than expected, and some skeptics of this system, suggested you would never even achieve that because of the sharp notch at that at this layer, where these layers are welded together. And this, represents a very small test sample, actually. This is maybe about 10% of a full fatigue test program. So there's more testing to be done. This was for an 1.5 inch thick sample in total. And so one thing that's not totally clear is whether the thickness limitations of fatigue details would still apply to this. And if so, if you took into account the thickness effect, this would actually maybe be an 87 design category. That's sort of to be determined. We could do some better quality control on the weld caps, and it'd be interesting to treat the weld caps and see at what point the mid layer does govern, if ever. So interesting results. Basically, the point of all this is to say, whenever we look at buckling, we're not seeing anything that would say this is a complete non-starter, the technology should not be investigated further. We're actually saying it's worth looking at from a finite element model perspective, and some of the early tests are showing that those models might be accurate. The fatigue test results, while just the beginning tip of the iceberg are showing promising results. Okay, so try to pull out of the weeds a bit, and so there's a different concern here when we're talking about supply chain, and so all of this multi-rep technology is interesting, but the technology readiness level is probably, it's not high enough for someone to invest $200 million in a factory to start building these kinds of towers. So we need something that's more adjacent to our existing technologies. So we have sort of reoriented the project to look at more advanced welding techniques and looking at this single rep technology, which brings us back to talking about like a 40 millimeter thick tower, but welded in a single pass instead of multiple. And this is kind of reiterating that concept that project development timelines, while long, 3 to 5 years, in order to get that initial investment, we have to have a deployable technology. So while it would be nice, and we're going to continue planning this multi-rep technology and investigating it further, we really need something investment worthy today in order to start delivering towers even 3 to 5 years from now for the offshore space. So we're looking at hybrid laser arc welding as a way to bridge that gap in commercial readiness. And so instead of having this multiple weld passes, you have a molten pool of weld bead, and you shoot that into the joint using the force of a laser. So you have a much different weld geometry. This is showing a conventional V joint, and for multi-pass welding, as opposed to like a hybrid laser arc where you're going to have a more rectangular joint, basically just flat pieces welded together. So the promise of this solution is that you can have much faster welding. So this is at least 50% faster than our current helical weld process. And this can weld single passes. What our research project is going to now investigate is 25 millimeter thicknesses in a single pass, which if deployed on our helical welding technology, we could basically do sub-arc on the other side of that and get up to 40 millimeters in a single pass. And then our cross welds would have to be multiple passes, but much fewer than conventional technology. And then this exists. Others are doing this. There are shipbuilders who are doing this in their panel fabrication lines today. And some of the benefits are that you don't get any sort of distortions, and your weld flaws are much smaller. This particular project, we're going to look at a U-groove. So 19 millimeters of this will be the laser weld, and then we'll follow that with a single pass of GMAW welding. And so some of the concerns are that you'll have some chemistries that are just not good for this type of welding, the chemistries of the base metal. There's, because of the small, there's less heat input overall, but it's concentrated in a much smaller weld, so you'll have hardness limits that you might be approaching, and embrittlement of that joint. So this research will fund the development of that weld procedure and the testing through destructive and non-destructive means. And then I kind of wanted, this actually came from that roadmap that INREL and Matt Shields put together. And so this is kind of talking about the marriage and the time that we have right now, maybe where some projects are pulling out of the plan, and maybe that's creating some space in the order books of some of the monopile suppliers, maybe. perhaps. So this concept of moving the supply chain further up the tower and the monopile suppliers being able to soak up some of that extra production might actually be a way for us to bridge this gap. I'm not sure of the latest details over in the Port of Albany, but I know that there's some possible, I don't want to talk too much about someone else's business, but there's some concern that this might not come to pass. And so without this supplier, there is no domestic tower supply chain. So even if we're supplying half of the towers, it's more than what we have today. Yeah, thanks.
Awesome. I just invite all of you guys to come join me up front here. Come on up. All right. I suppose we're gonna need this, correct? Okay. Let's do this. Yep, good. All right. So I hope you guys are feeling a little bit smarter certainly about towers and maybe large rotor castings. I know I am. Actually, maybe I'm sort of have all these other questions. So I am going to actually ask each of these two gentlemen on the left a quick follow-up just from me. So the first one, and we will also see what you guys have on the Slido in a little bit. Keep an eye on time. And where's Corey? Someone just flag me if we're getting towards 1:45, and we haven't pivoted. Srikar, the project that GE is looking at, these large rotor castings, the premise is by segmenting them into 3 or more parts and then welding them back at the nacelle production site is going to open up suppliers domestically. Is that the premise?
Right, that's one of the pathways,
Yeah.
yes.
So I guess my question is, not knowing much about large casting foundries, what does that sort of supply chain look like in the U.S.? Are there like 3 of them, or are there like 36 of them?
Yeah, so before I answer that question, so a little bit of background on, what really started this discussion on our side was, how we approach some of the large castings today, right? So there's a hard constraint around the bounding box of a given component that you could transport by road, and that's roughly around 4.5 meters. So if your part is larger than that, then, even if you're able to make it in one monolithic shape, you have to cut it down to pieces to transport it. So bolting is one way that folks go around to assemble, and that's an existing practice today, right? So, but there's a lot of challenges around bolting. So the design gets complicated. You have to precision machine, needs to happen, and all of that goes in. So there's a certain logistics and design, pain point that could happen because of it. Not to say that, it's not done today. It is done today, and it's done very well, right? So the thought was the alternate form of joining is welding. Could you weld it and assemble it together? And that becomes tricky for material reasons and, that as well. But then if you were to crack it, if we solve the certification and qualification challenge on this program, then the thought was that could pave a path for a new kind of, design philosophy where you could explore segmenting large castings to small ones, so to segments. So the idea there was you may not need, or you could rely on a network of smaller foundries that have, per capita smaller pore capacities to make the parts in pieces, and then you have it assembly somewhere. So the thought was, could you decentralize the manufacturing among a bunch of smaller foundries, right? And in theory, that sounds like agility, that sounds like flexibility, but does the cost make sense? So that is something that we haven't explored yet, right? So when it comes to your question of how many, so there are not a lot of foundries in the United States right now that could pour an offshore level component in a single footing. I think there is Hodge Foundry somewhere in Pennsylvania. I think there's St. Mary's, there's a couple of them, but that's it. So I think in the United States we were able to do this a lot more in the past, but I think but eventually that's where we are today, right? Small foundries, I think there are more, but even considering what we have on hand, I think there's a large need for new construction, greenfield, brownfield foundries to kind of come into the States too, if we had to ramp up and imagine a truly local domestic supply chain for these castings.
Excellent. Appreciate that. Super helpful. Quick pause here. Corey gave me explicit instructions. Oh, am I going up? No. Oh, there we go. Don't want to let Corey down. It's a lot of responsibility. Thank you. Appreciate that, Walt. So Eric, all right. And I think you started getting after this toward the end of your presentation. I followed about maybe a quarter of what you had to say, but I'm sure there are other technical experts who really appreciate that, and it's good stuff. This is innovation. Trying to drive solutions and lower costs. That's why we're here, and that's the mission of now RDC. So I guess my question is just sort of thinking about that sort of shared scope where in an ideal world, or in Keystone's and others' ideal world, you are doing that spiral weld for the top tower segment. And I assume you're doing that close to on site. Is that correct, or maybe not? Maybe that's another premise. Let's not go there. Let's just start sort of a higher level. What is your sense in terms of sort of cost savings? That what is the value proposition that presents for developers and really the turbine manufacturers?
Yeah, the value proposition that remains in the offshore space is really throughput on factory footprint. So we can fit our factory into smaller locales, smaller acreage footprint than a conventional tower supplier. And so, yeah, waterside ports are expensive and limited, and so that is the benefit. We can go where the demand is, and that might fit into some of these economic development zones or preferred workforce development areas also.
Okay, great. Appreciate that. All right, a couple questions that I've sort of teed up for everybody, and I'm going to ask each one of the panelists to sort of just offer their take. This first one is actually something that I've been thinking about, but I did see it sort of captured in an interview with David Hardy, Orsted, and E&E News. And it's a good question, and it's sort of framed as this: the offshore wind domestic supply chain is a bit of a chicken and egg problem. And hear me out here. So the turbine and component suppliers, they need more projects, they need order books, they need a strong market pipeline in order to justify the millions of dollars of investment in these local manufacturing fabrication facilities. Developers need more local suppliers in order to help address sort of cost and deliverability. So, there's some tension there. They're both sort of aligned, but it's a little bit of what comes first type of thing. So, and you don't have to sort of address the framing of this, but I'm interested to hear what each of you would say are the 1 to 2 critical ingredients to establishing the tier 1 local supply chain here in the U.S. And Walt, why don't we start with you?
I'll use your mic, still on. So big picture, I think, is what I look at when it comes to this question. The one what we have to do is create market certainty and visibility long term so that the manufacturers who are thinking about investing in these factories and the supply chains have some assurance that their investments will be enduring and durable for many years. And I think to do that, we need to, I think the states can play a big role in how they structure their procurements to make sure that the supply chain that does exist and that is protected, and that the new supply chains are being built to serve these developers, because the developers don't have control over the supply chain investments that they're counting on. So I think that's a big part of it. I think one thing that the industry can do, and I think we're going to need to put our heads together on this, is how to control turbine upscaling, because there's each time we go to a new technology platform in turbine size, we have to build a new supply chain, and we can't keep doing that. We have there's many examples of industries that have had to limit their growth and their size by simply staying where they are because the infrastructure to support that doesn't exist or can't be built. So I think those are at least my two big ones that I would put forward. Maybe I can pass it. You guys have one?
Yeah, so I echo what Walt said, and I could add to what I'm thinking about on the casting side of things and things like that. So I guess agility and flexibility would help overall in the supply chain, right? And I think just a replication or a traditional way of approaching a manufacturing, I think, is also challenging and perhaps even cost prohibitive. Because I think one of the big factors we have to kind of tackle head on is that labor costs are pretty significantly different across the globe. And if we have to, rely on a domestic supply chain, we cannot be, going through the manual processes or set up a labor-intensive process domestically. That'll just make it cost prohibitive and not sustainable in the long term. So automation is key, I think. So I think there's a need for advanced manufacturing technologies, increase for automation, and when we set up something like that, we have to be kind of holistic in thinking about not just one product or one platform, but rather setting up in a state in a format where we could stomach that variation, not say impose modularity on everyone across, but develop solutions like that. So I think in the long term, we'd have the buffer to tackle such uncertainties. Yeah.
Excellent. So let me just clarify. Did GE just commit to not scaling up to the next size? No, I didn't think so.
That's beyond my pay grade. And,
Yes.
I don't think I can say anything to that. Yeah.
All in jest.
Yeah.
Yeah. Eric, thoughts?
Yeah, and I think you maybe have questions that get to this, but the regionality, that's something we always talk about. We can't have a tower factory in every state. There's that piece. Obviously, yeah, if we can kind of have a flexible boundary of that, where that supply chain is, as I'm sort of promoting here, maybe we walk down that line as we bring on our multi-wrap technology, and the supply chain is getting pressured with, I'm thinking like closer to the 2030s, maybe there's more demand, and so the monopile guys are going to stay in their lane more. So that if being able to move that boundary a little more flexibly is one way you keep the supply chain resilient, but keep that pipeline full for all the parties. That's kind of my 2 cents on that.
Let me just clarify by boundary. What do you mean by that?
Yeah, so what I'm saying is, like, in the very near term, Keystone can supply tower tops with our adjacent technology. 10 years down the road, when turbines are larger and we've developed the multi-wrap technology, maybe Keystone, and there's more robust demand, maybe Keystone slides that down to the full tower, and the monopile guys supply monopiles. That's where I'm saying,
Yeah,
move
and
the
scope.
supply chain.
And scope between foundation and
Yeah,
tower.
the
Got it.
scope, draw that boundary
Yep.
differently.
Yep.
Yeah, I want to follow up, putting on my kind of my now RDC hat now. I think both of these guys are developing products and innovations that promote domestic content. And I don't think you necessarily said that, Eric, but I think there's an advantage to being able to use thinner steel sections so that you don't have to import from outside the United States. This is domestic products, and I think the same thing is true from the castings. Is we're trying to build enable someone to build these factories that they couldn't really build in the past. So, has there been any development or thinking around the idea that if you could promote this domestic content, then there could be advantages from the policy side on how one might take advantage of that domestic content, like, for example, with the with the Inflation Reduction Act that offers a domestic content bonus for some of that stuff. Has that come up in? I didn't hear that mentioned, but has that part of your thinking?
Yeah, for me, yeah, it was implicit to my thinking, so maybe I didn't just advertise that, but yes, yeah, it's a American-made company with a domestic supply chain, and yeah, of course.
Wait, quick follow-up, and then I'll give it back to you guys. So what about sourcing steel? Just quickly speak to that, because obviously that's part and parcel to this domestic content conversation.
Yeah, that's a little outside my wheelhouse. Other people deal with that. But yeah, I know we have domestic suppliers. I mean, currently we source coil, hot rolled coil, and it's all domestic. And there is, there's some carbon content of the embodied carbon of that domestic steel supply chain too, for those people who care about that. Yeah.
Yeah, so yeah, we think about Inflation Reduction Act too, and I think again, my proximity to all of the business end of things is far, given that I'm at the research center. But I think the production tax credits and the emphasis for taking on local content, I think that's through, and it's a partnership between GE and the suppliers to can do it. And your question about tier 2 suppliers, who suppliers, our tier 1 suppliers, where is that content coming from? That's also an important question, I think, and that comes up during discussions all the time too, because, yes, the end product is made locally, but what about the precursor that goes into your end product, right? That's also something to think about.
That's a great segue. So my next question is sort of focused on sort of tier 2, tier 3, tier 4 suppliers, and just pointing back to the excellent work that Matt Shields and the NREL team have done on the supply chain study and reports and the roadmap. They find that the jobs and economic impact from the tier 2 and 3 suppliers outweigh the jobs and impact from the tier 1. So there's something significant there. The other thing is that, and you guys touched on this, and Walt did too with some of his slides. There are tier 2, 3, 4 suppliers throughout the continental U.S. In states that may not have offshore renewable energy goals, but businesses that I'm sure would be more than happy to participate. So I guess the question is really about activating tier 2 and 3 and 4s, and we spend at Mass CEC a fair amount of time sort of thinking about this and working with developers and others in the Commonwealth, trying to make those connections between buyers and suppliers. So I think the question is twofold. Number one is, what do these suppliers need to do to be able to get ready? And that could be from an operational and a capital perspective. And what can we do to support that, either from the private or public sectors or others? And just to add a twist to it, not to make this more complicated, but hey, why not? What about this sort of timing question, right? So this industry keeps going like this, right? Stopping and starting 2 steps forward, maybe 1 step back or half step back, depending upon who you talk to. I'm a tier 3 supplier. I need to make some investments. I need to pass up maybe other business opportunities. When do I make that decision? So anyway, there's a good one. Walt, you want to start?
I'm not sure I can add a whole lot more to what Matt's already done because they did such a great job. But I think that what I go to immediately is, we need to reach out and educate those suppliers, because there's thousands of them, and they may not know what we're trying to do. So we need public education, and then we need workforce training, I think, to adapt their skills, because the skills are pretty much there. They just need to be tweaked, and then there's probably production facilities that need to be augmented. But these are the areas where perhaps it's low-hanging fruit, because there's less large-scale investment that has to be made necessarily to get those factories and those workforce members to participate. And I'll stop there, because I don't want to start speaking out of school. I probably already did.
That was good. It's fine. Srikar, any thoughts?
Yeah, so I think that's a very difficult question to answer, honestly. But just speaking of personal experience, trying to build consortia around castings and interacting with suppliers. So kind of my 2 cents, I guess, is that you brought up opportunity cost, and I think that's a big deal for some of the tier 2 and tier 3 suppliers who often operate at very small footprints. So for them to be thinking about such big picture is often very challenging. But again, education with regards to the opportunity and the growth, I think that has to be organized at a much high level, and the problem perhaps has to be simplified for them. Yeah.
Let me follow up. So you're talking about working with DNV on a qualification.
Right.
And is that for the weld scope or the casting scope?
It's for the welding.
The weld scope.
Weld scope only.
Would that be, how high a bar would that be? Would that be something where the sort of GE and your suppliers, for a supplier to engage and to receive that qualification, sort of what is that? Or maybe you don't know yet, it's still in development, but is that a high bar? Would they benefit from the assistance of, let's say, a manufacturing extension partnership type of program? Just one quick follow-up, if you would.
Yeah, so I think the short answer there is partnership, right? So it's when we're trying to, it's going to be some kind of a technology, partnership. So in the past, just discussing technology transfer, something that we've developed internally, taking it out of them. So there's a lot of factors that go into that kind of analysis. So it's truly a partnership. We go into the discussion with certain improvement in the process. Now, what are the advantages, or what is the outcome that's expected out of incorporating, say, a new technology? There never is a single solution to that problem. They're often open-ended, a lot of things. The supplier could come back with another solution that achieves the same outcome, but doesn't necessarily use the same thing, right? So that's the thing. So it's a partnership. So we hope to initiate a conversation, push the needle beyond what is out there today. But the outcome is that we want to make the supply chain more resilient. We want to incorporate more people. I'm not saying my idea is the only way to do it, right? But then steering the conversation, and that's how we build partnerships.
Excellent.
Yeah.
Appreciate it. Eric, thoughts?
Where I'm thinking is flanges come to mind. So we buy our flanges. I don't believe there's any domestic supply chain for offshore scale flanges, and yet they would probably be classified as structural steel, which is how you get the investment Inflation Reduction Act production credits. So like that's a piece where if flanges are required, but we don't have any domestic supply chain, then the whole implicit assumption that I'm getting these credits just falls apart. So that needs to be clarified. I'm sure that's not the only piece of this, but that's the first that comes to mind.
Yeah, that's a great, very specific example. All right, I am going to pivot to some Slido questions. There's a ton here. This is just kind of be a little bit of sort of free form because I don't have the multitasking capabilities to review 20 questions and prioritize them. But in looking at these, there's a couple here that are really specific to Eric and the tapered process. So let me read two at once, and you can we'll get a twofer. All right. So yes, I know this is like in real time. How would tapered welded towers be connected into the transition piece? Same conventional bolted connections, or would there need any sort of special connection? And how does a tapered manufactured tower compare in terms of stiffness with the same dimension as the conventional tower? And I think that's where you're going with some of the studies you're doing.
Yeah, so currently everything in the offshore space would just be a direct drop-in replacement. So all the interfaces are identical. So there'd be some collaboration with other suppliers to make sure those interfaces align. And then, yeah, the strength is identical, especially if we're doing only the tops, identical thicknesses and everything like that.
Awesome.
Yeah.
All right. I guess maybe this is sort of a question on welding that's back to GE about advanced welding technologies. And I know, Eric, you talked about the hybrid laser. So, Srikar, I don't know if you want to respond, but sort of what are you guys looking at in terms of advanced welding for the large casting connections?
So we're starting with metal inert gas welding, and we also have the hybrid laser arc welding as well, or just laser wire welding. We're looking at all of them, but the end decision is going to come from the techno-economical analysis, because the capital expenditure in setting up this equipment at foundries or at assembly plants, and the material cost that goes into performing these welds, all of them play a role in which particular technology we want to shortlist. But at the end of the day, I think the innovation we're really pushing for is automation, not necessarily around the modality that we use for welding itself.
Okay. All right. This one is going to be a toss-up here. How can universities help address supply chain issues, both in terms of research, and the example is here, development of regional research centers, as well as workforce development? Anyone?
Sure. I think you just answered it, but I think that universities are well placed for workforce training and workforce programs. I know from our standpoint, someone who has the basic knowledge of wind energy technology is going to be a lot more marketable in the workforce. And then, even if you're doing a specific part of the workforce component or something, it's still helpful to have that broader knowledge. So I think there's a program at UMass that has for a workforce or an offshore wind certificate. I think those kinds of programs can be expanded. I mean, a lot of places can have that. Northeastern has some programs now that are expanding, and I know, I think there's a need to just broaden those in general. And we're definitely going to need. We don't have enough people to do what we want to do right now, and I think we're starting to get there. But I think that the problem is enormous, and we need to keep going. Yeah,
I echo what Walt just said. We at the research center, we partner with universities all the time, build consortium around solving, the R&D problems pertaining to supply chain. And one of the, broader impacts that we're shooting for on some of the programs that are, much closer to end application is, again, workforce development. I think building the curriculum straight out of a research collaboration and perhaps partnering with the two-year colleges, building something like that, I think, is a couple of paths that we've taken recently. Yeah.
Okay. Eric, do you want to add anything to that?
Oh, I'm good.
Okay. Yeah, I mean, it's very clear from what you guys presented that university partnerships are critical and core, you might say. So, yeah, in some ways, maybe that was a rhetorical question, but a good one. Maybe one just sort of observation on that topic, sort of workforce and really specific getting, I know when we work with our workforce educational and training provider organizations, they are really looking to industry to help define the credential, the, curriculum, really the specifics that, by occupation that we are collectively going to need. And we start to see a little bit of that in the roadmap. And I guess maybe from some of the slides that Walt presented on behalf of Matt, that some of that NREL work for the Mid-Atlantic will sort of dig into that. But I guess I'd put in a plug, as you guys are, you're still talking about automation, but you're still talking about technical engineers and other laborers to oversee even automation processes. To the extent that we're able to come together with cross or adjacent industry specifications and credentialing is going to be really, really important. So it wasn't really a question, maybe more of an observation. I've got a couple here. They're somewhat redundant, so I'm going to jump down to one I had, which Walt sort of mentioned in one of his slides, and it's something that is I think in everybody's minds as they are looking at making these big investments, or even if you're a tier 2, a modest investment, but for you proportionally probably just as big. This concept of pipeline, boom and bust, are there sort of diversification, adjacent sectors? Are there sort of policy drivers? What strings can we pull to really try to avoid that situation where you are having these big dips and cycles where some of these production facilities have to go dormant for a period of time, and that has cascading effects. Walt, any thoughts on that one?
I mean, it goes back to creating predictable markets and predictable supply chains. And I really think, that a lot of the disruptions we've seen recently will self-correct the macroeconomic changes, but the supply chain stuff is on us. We have to build the supply chain, and we have to make it robust. And I think the dips that you're talking about are going to be created by supply chain deficiencies that we'll see, especially, one example that I would use is the Ørsted project cancellation in New Jersey, where that project is had made commitments, and no longer those commitments are no longer there. So there's going to be now, will those factory? I don't know the details, but that's going to cause a ripple effect in vessels and ports and monopile manufacturing and turbine manufacturing that has to get filled somehow. And a lot of the projects that are being canceled and have to be renegotiated, as you well know, because it's happening in Massachusetts, Connecticut, Rhode Island, New York, New Jersey, all up and down. I think we're recovering from that pretty well, but that's going to delay projects, and they're going to pile up later on, and everybody's going to want the supply chain later, but not right now. And then so so there's going to be this surge that may not get met, and then no one's looking beyond that. So there has to be a long-term visibility that says, well, we're not just talking about 2030, we're talking about 2050, and we have to start to together maybe smooth out those ups and downs, because it's not going to be possible to make 10 gigawatts one year and 2 gigawatts the next year. We have to have a nice ramp up, or at least ideally a steady production line that keeps going. I don't have the detailed visibility on that, but that's what we need to do. Anything else?
That's good. Well, I appreciate that. I guess maybe one reaction, one thought is that I think a lot of folks have learned, and we continue to learn as we go on this. And I'm optimistic that the procurements underway and anticipated from the states you just mentioned will in fact result in a reset and a growth in pipeline, and PPAs or offtake contracts that are more durable and perhaps more flexible to allow for some of the sort of volatility hedging. And it's not perfect by any means. But in Massachusetts, I think we have tried to signal to industry that pipeline through a couple different ways. One is we talk about our legislatively authorized procurements, so 5.6 procured by 2027, and we know the legislature is working on sort of the next derivative of that. But we point to our roadmap and all the work we've done through the decarbonization scenarios, looking at what does Massachusetts need and what does the region need for our decarbonization and load transfer. And that's, there's lots of different numbers out there, but the number we're sort of currently floating is 23 gigawatts. So, and we sort of look at, some of the supply chain constraints, such as ports and deployment, and the ability to sort of do, 2 gigawatts a year as being sort of a cycle that, we can, sort of work towards. And that may get a little bit larger as turbine scope increases. But that sort of lays that out. The other we've committed to is doing these steady state sort of frequency procurements. So in Massachusetts, that's every 2 years, and we've stuck to that, and we see no indication that that will change. So these are the things that we're trying to respond to the market to indicate. So I'm not seeing a lot of new, fresh questions here. So unless someone wants to jump up and down and have that burning one that wasn't answered, I'm inclined to thank our panelists and give you guys an extra 5 or 10 minutes and call it a wrap. Anybody? Last questions? All right. Thank you guys very much. Thank you all for joining us.